Dr. Yisul Jin. He is from South Korea. He obtained his master's degree from the University of Colorado, USA, and PhD from Southern Illinois University, USA. He has been teaching geotechnical engineering at Incheon National University, South Korea. Currently, he is the director of Creative Educational Program for Future City Design, which is supported by Ministry of Education in Korea. He is also a Vice President of ISSMGE, International Society of Soil Mechanics and Geotechnical Engineering for Asia. Professor Sin's field of specialization is geosynthetics, geotechnical, geo-environmental engineering, shallow foundation, and ground improvement. He has published 5 books on the geotechnical, geo-environmental, and civil engineering related subjects, as well as more than 100 journals and number of conference papers. Currently, he is in editorial board of member of Journal of Geotechnical Engineering and Journal of Geological and Geotechnical Engineering. He has been an editor of 4 conference proceedings in international conferences. Today, he will be presenting a lecture on innovative shallow and deep foundation systems in weak soils. I invite Dr. Sin to present his lecture. Thank you.
I think it's a special privilege for me to deliver the memorial lecture on 25th anniversary of the Nepali Geotechnical Engineering Society inauguration. I think this is the 3rd time to trip to Nepal. And the first time I came here in 1999 as a tourist, and with my wife. And the second time we had the MOU between our university and the Nepali Geotechnical Society, 2016, right after the 2015 Nepal earthquake. So I brought a student, 10 students, work at the Gangneung County for rehabilitation of the earthquake damaged water supply line. So today I'm going to talk about innovative shallow and deep foundation system in weak soil. I think this technique can be used in the Nepal, so that's why I brought this this topic. There's a honey cell foundation. This is like kind of a reinforced shallow foundation system, and the second one is like a deep mixing or deep ground improvement method. They may play as a role of the foundation reinforcement or some supporting pile for low and medium high rise building. Oh, this is a panoramic view of Incheon city where I am from. All this land reclaimed the soil from the sea. So because of the South Korea as a peninsula, but South Korea also divided by 2, North Korea and South Korea. So we have a problem, to gain the sufficient land to develop the industrial complex and also residential area. This is our school located here, and about the right hand side, and all this Central Park is man-made. So of course we use a lot of geosynthetics, geosynthetic clay liner, geocells, and geosynthetics. Okay, this is called Central Park, and all this area we have a high-rise building and medium and low-rise building. So reclaim the land like a silty sandy soil. So how can you accommodate foundation system for this? Because if you have maybe some small building, lower building, if we use by foundation that goes up to here, goes down to about 28 meters. That's very deep, you know. But it does not necessary. The stress doesn't go up to that depth. So we may need an alternative foundation system. So we propose, you know, the honeycomb shallow foundation. I think all this, you know, man-made land, maybe you may build another, you know, like New Delhi, new, you know, Kathmandu or something, you know, suburban city, because there's too much congested here, Kathmandu city. So I'll talk about the honey cell foundation. Like this is a modular block type of the reinforced earth, you know, shallow foundation, and we do some theoretical background and the experimental test and numerical analysis we will carry out. So this system is suitable for the weak soil, and also we carried out experimental work in the laboratory and also field test and also practical application and numerical analysis, and we found out this is a very cost-effective method to improve the ground. This is a honey cell. Normally that 4 cells together, you know, there's a one set, okay? And if you look at the left-hand side, and there's a virgin ground, and then we placed about 30 centimeters of the crushed stone. And then above that, we have a honey cell, okay? Modular block, hollow, hexagonal shape of a hollow space in the concrete block, and we fill the crushed stone. After that, we put in the like a cap, no, concrete or something, no. Yeah. After that, the lean concrete and the real foundation there. I think this is very, you know, easy to work. And so the modular block is one single block, doesn't have any big power. But if you have a continuous block, and see here, I think the sequence of the construction work for excavation, we need a bracing system. See here, and then we place the crushed stone about 30 centimeters, but depends on the underrange strength of clay. Okay, you do bench test, you find out the underrange strength, you can determine the thickness of the aggregate layer, okay? Then we compacted, roller compacted. After that, we place the honeycomb cell, then fill the crushed stone. After that, we can do another consecutive procedure. Why this cell has a great advantage? As you see, on the top, maybe there's just a crushed stone layer, but that doesn't have any much frictional force. But the bottom one, the frictional area in the hexagonal shape in the side wall, or then about 3.6, was compared with the top and bottom one, about 3 times greater frictional force created by this modular block type of the foundation system. And mechanism of the failure envelope. This is the first term. I think there's a frictional force inside of the modular block. Okay, first term, the blocking, and second term is a weak soil layer. It's a general shear failure for clay and some local shear failure, and then last one, the block, is the bottom of the footing, okay? That related to the that passive earth pressure, that PP with the angle, inclined angle, delta, with respect to the depth. So this is pretty much, and this is inside the block, the shear force created along the modular block inside the hollow space. Of course, we can use that under the block. We can use the constraint modulus instead of Young's modulus. We can use the constraint modulus for the bearing capacity. I think this is the typical that strong, the sand layer over weak sand layer. So we don't have any the C tone, So and also we dropped here the frictional force inside of a modular block to have a conservative, that way. That is similar to the Mayer Bahana. They presented the formula 1978. Mayer Hoppe, he did a lot, entire his life, he researched on the shallow foundation work. So that's why my former professor, Professor Das, he got some lesson from the Mayer Hoppe. So he did the shallow foundation work. And we can combine all those formulas together, and then we can present it, the bearing capacity formula. And as you notice, case of S, there's a puncture resistance, along the shear failure, the bottom of the aggregate layer, and you can get from the textbook. So we did carry out some, the laboratory test with that hollow, the cylinder about the diameter 1 meter, and we use two blocks. One is a hollow hole, the other hollow space. The other one is not hollow space, just plate, Okay, and then when you find out, interface friction angle in the hollow, you need we use the two different material. The left-hand one is sand. Right-hand one is a crushed stone. So, the combined pressure, we should apply the appropriate in the range, okay? Sand is a little bit low level of the combined pressure, and the right-hand side is a bigger range of the combined pressure, which influence to the frictional angle and also apparent cohesion. We use the pretty big size of the direct shear device, 30 cm by 30 cm, left-hand side, the sand. And crushed stone, we use the 50 cm by 50 cm. We hydraulically load, and hydraulically we push the shear box. Okay, so that we got right value. We found out. So we use the all these design, and we have several different, the category of reinforcement. One is just a hollow without sand filling, and the second one the crystal stone in the bottom layer, and also inside also we put in the crystal stone, and the last one we didn't put in the feed in the aggregate in the hollow space. Then we found out our bearing capacity. We determined, I think this is normal practice in the first one. The model C, which has a crystal stone field, and also the bottom layer, there's crystal stone, which gives the highest bearing capacity, and the settlement level is very small compared with the other case. And we found out all the above the bearing capacity, and gives lower settlement level. And we did like the situation, plate load test, 1.5 meter by 1.5 meter. And you see the SPTM value is very low, and so 1 or something. And then we compare original ground, which gives almost same ultimate bearing capacity, but original ground which gives a higher the settlement level compared with the Honicell, the foundation system, and also we did some numerical analysis, and we compared the plate, the foundation system right-hand side, which has a great amount of the settlement compared with the left-hand side, Honicell, and also stress reduction layer, and Honicell, which gives higher the reduction layer compared with the met type of the foundation system, and also that spreading. Honicell has a very much spreading, the pressure distribution compared with the left-hand side, which has a much greater vertical direction of the stress distribution, which creates the much higher the settlement level compared with the other one. And also this is the same theory. And also we did the field test. As you see this field test, the honey cell, they're about 7.5 millimeter. Another one is original ground about more than 24 millimeters that allow settlements about 1 inch, 2.54 centimeter. And also settlement level, that analysis also similar result we have. And now this is the case history, Samsung electronic, plant. I think that's very sensitive, They had a very original, the foundation system pile, the high strength concrete pile. And we have the N value there. And we modified to the right-hand side, the honeycomb foundation. And we found out, there's no problem for this. And this is a sequence of the work here. And this is filling the gravel. And on another side, we do some, I think this 5 stories building, okay? That's clay soil. Also reclaim the land from the sea, that all clay, soft clay. As we say, M value, some value, and 3 or 4 or 5, and then we do a bearing capacity test, and we found it out okay. And let's move, So that honeycomb, like that foundation system are suitable. About M value, maybe 3, 4, 5, 6 would be okay, But 7, 8. But the number of stories, maybe 5 stories. 2 stories, no problem, 5 stories or 6 stories, Up to that, maybe okay as a safe side. And point foundation system, little more safer, a little more deeper, the reinforcement. As you see, this is not pile, and so this is it. Normally, you see that normal practice in Songdo, in our the city, we use like a high strength concrete pile up to maybe 28 meters or 30 meters. Or another alternative way, maybe basal foundation system, like this second one, basal foundation B, and maybe cannot prevent any higher consolidation settlement, right? Because below in this soft clay. So that's an alternative way we propose. Intermediate, foundation system. On the top soil relatively higher strength because backfill soil, following material. So we make an enlarged diameter, 1.4 meters normally. After that, we have a cone type. Then the lower area, taper area, about the diameter 60 centimeter. So the end of this bearing line, M value about 18 to 20. I think we recommended. Then is no problem. So then we can have a very good increase the bearing capacity. Also, we can eliminate the settlement. So this system, and also we can little bit adapting cap, so that we have a cap system surface about 0.2 to maybe 2 meters or something, So you can have a good that foundation system, so that they can use, so we have a first bearing ratio, second bearing layer, and the third bearing layer. Okay, so by using this and the calculation of the bearing capacity, okay? So we adopted like improved ground. So we normalize all the shear strength, unit weight, or frictional angle, or so on. So we put in the Terzaghi equation and the Mayhop and the Hansen's, okay? So we consideration of the load inclination, the embedment depth of foundation, and also shape of the foundation. And we calculated, we selected the lowest one, okay, smallest value as a bearing capacity. And the settlement, we have a top layer and the enlarged area that we also calculated elastic settlement and the consolidation settlement. And also bottom layer, taper area, also we calculate consolidated settlement and also the elastic settlement by using the Smartman and the Hartman, 1978. Okay, that's a very common practice. So we compare that, and this is equipment. I think you are very much familiar. There's a small equipment we can use, and the medium size, much deeper, maybe 40 meter or something. And the right hand side, that's the equipment. Okay, that's the. So you can easily, following this, system. I have all data here in the computer, So you can make like this device right hand side, and you injected the cement milk and mixing it. Okay, so you can make a good foundation system you can use in the Kathmandu, Okay, so that is the mechanism. And compared with the time consuming using the deep foundation system and this one medium size, deep mixing system, this is about 5 minutes, about 5 to 6 minutes. That's 12 minutes for installation of 6 meters, depth of pile. And the right hand side, on the top, about 25 minutes, So that takes a longer time. This is left hand side is the construction work site, and the right hand side is more PhD pile, They're very messy, You need a lot of equipment for that. So for low, medium-sized building foundation, fantastic. That's another alternative way. There's another advantage. This is we used in Vietnam. I think the last year we used, and about 4.5 meter steps, and we calculated the bearing capacity and also settlement level, which is the meter requirement, less than 1 inch settlement and also bearing capacity. And we did field test, okay, about 750 kilonewton per meter square, and we have a satisfactory settlement. And also, we shouldn't forget the integrity of the body. This body, unconfined compressive strength, axial load, shear force, and also the bending, okay? So we all calculated, and that satisfied the requirement. I know the Vietnam is a very soft soil they have, So we got very careful, but we found out, So this is several category we can use for this, point foundation system, okay? Different category. So I'll show you the field. I think this is one of expressway. We have a box cover on the top, so we need a ground improved, So we use a point foundation system right inside, and the box cover to 5.5 meters, very high. And the sequence 1, 2, 3, 4, and finally we do static load test, which can create the make sure the bearing capacity is enough or not, and also we digged out the diameter they really formed or not. And another site, Busan. Maybe you may not familiar. Busan is a very soft clay up to 60 meters or so on. Okay, very soft. So we use that, that improved. No, they already improved, but they expect another additional settlement. So we put this, foundation system prior to put in the structures, over there. And also, it's another Busan's port site. And this is another near to Seoul, because of that along the riverside road is fully saturated. So we now construction underpass, another highway under the ground. So we have a box covered, right? So we got the ground improved. So we use this method, okay? So all these, So how many meters? 5.2. I think it's quite a bit, that work. And this is working, Just next to right, improvement of the ground. There's a right hand side. There's very heavy traffic is on the way, and we clear it and make sure the by load test, so static load test to have enough bearing capacity or not, and also this our town Songdo, there we have about 10 stories building. We use this foundation system right there. So embedded about 18, 20, like this. So some places we want to have some like underground parking lot. So if you have apartment complex, you need underground parking lot, maybe like a first layer, first basement, and the second basement, third basement. So we need a little bit steeper ground improvement. Otherwise, for apartment we have a very lengthy pile foundation, but the parking lot is not improved. Then you have big problem. So we have pile foundation too much expensive. So we use this alternative foundation system, and we found out shallow foundation, modular block type foundation system is very suitable, maybe up to 5 stories, 6 stories building, and with the M value maybe 3 or 4, 5, 6 or like this. And the interlocking force, shearing force is created greatly. I was surprised by myself. And also a point foundation is a very suitable alternative between pile foundation, maybe the shallow foundation. There may be more safe side. I think Nepal it could be good, a solution for medium size, like the building construction work. Thank you very much. You pay attention. Thank you. Namaste.
Thank you, Dr. Sin.